Hello. Good morning. Welcome to all the participants to this interesting parallel session that we have for the first time in the Marcel Grossman meeting. Hope this would be a seed for the fruitful future of this field in the physics, and especially in the astrophysics and the related branch of physics. Okay, I think we can start. We didn't expect for so many participants, so we are very restrict on time, and we would appreciate if you can finish on time. And for each participant, we have around 20 minutes. So it would be appreciated if you respect this timing, and at the end, or if some participants finish their presentation, we can have some short questions, or at the end we can have some more questions from participants. Okay, Dr. Yu, if you have something to say.
I think let's start now because already 2 minutes past.
Okay.
With very limited time.
So first participant, first present would be Fateme Rastegarnia, and the title is Deep Learning in Searching the Spectroscopic Redshift of Quasars. Okay, we can start. Can you turn on your voice also? Microphone?
Hello, can you hear me?
Yes.
Okay, shall I start?
Yes, please.
Okay, hello, my name is Fatema Rastegarnia. I am a PhD student at Al-Zahra University. And here in ICRANet, Pescara, I am a visitor. In this lecture, I'm gonna talk about deep learning in searching the spectroscopic redshift of quasars. This work is done in collaboration with Dr. Mirtorabi, Dr. Moradi, Dr. Wang Yu, and Dr. Wafai Sadr. Here, for start, I'm going to give you a brief introduction of quasars, and after that, I will explain spectroscopic redshift, and I get through the SCSS data set, which is utilized in this research, especially DR16 quasar only, and I will explain the data preprocessing, and after that, I will talk about FNet, which is the convolutional neural network that we created to solve this problem. Quasi-stellar radio source, or quasars, are high luminosity active galactic nuclei, which are believed to be powered by a gaseous accretion disk around a supermassive black hole with masses in the range of 10 to 6 solar mass to 10 to 9 solar mass. Thanks to their high luminosity, quasars have been found to spread from redshift approximately 0 to all the way back to a redshift approximately to 7. When the universe was forming its first structure, namely the epoch of reionization. So study the high redshift quasar can be taken into account as a powerful tool to study the cosmic history and the structure formation in the early universe. Spectroscopic analysis indicate that emission or absorption lines from quasar are significantly different from the spectra of stars or galaxies. In fact, the spectra of quasar contain bright UV flux, broad emission lines, and oftentimes variable flux, both in continuum and in the emission line. Quasars were first identified during the 1950s as a sources of radio emission of unknown physical origin. And when identified in a photographic image at visible wavelengths, they resemble faint star-like point of light. In 1963, Martin Schmidt, the guy that you can see in this picture, recognized that the spectrum of the 3C 273 quasar can be interpreted by the redshift of 0.16. Here we have the hydrogen spectrum of quasar 3C to 173, and the redshifting is obvious here. Subsequent work by Schmidt and others led to increasingly large measured redshift and recognition of the broad class of active galactic nuclei, AGN, of which quasars occupy the high luminosity end. Schmidt's discovery and change extragalactic astronomy in a fundamental way. In this slide, I want to draw your attention to one of the most recent research which emphasized the crucial role of the quasar in high redshift cosmology. In this graph, in this plot, we can see the distance modulus to redshift relation of quasars. And for redshift less than 1.4, this relation is agreement with the type A supernova, and it is in agreement with the standard model of cosmology, lambda CDM. But for redshift greater than 1.4, we have deviation from. As I mentioned, quasars are most luminous sources in the universe, observed up to redshift approximately 7.5. So it's worth to study quasars in order to study the early universe, where the universe formed its first structures. And also, quasars are perfect tools to study the physics governing the formation of supermassive black hole and their surrounding accretion disk. Here we have quasar rest frame wavelengths, and you can see the prominent distinctive emission line here, like Lyman alpha and MG second, which is very useful to spectroscopic redshift estimation. Actually, in a spectroscopy, by observing the full spectral energy distribution of quasar, one can detect this distinctive emission line that can lead to a redshift estimation by measuring the wavelength shift to this spectral characteristic from the rest frame. Due to noisy observation, the main redshift estimation methods involve cross-correlating the SED with the predefined spectral templates or PCA decomposition. I mean principal component analysis decomposition of the template library. A noisy condition and potential errors due to the choice of templates are the main reasons that the most reliable spectroscopic redshift emission methods heavily depend on human judgment and experience. Among the optical survey of quasars, data release 16 quasar-only database of SDSS extended baryon oscillation spectroscopic survey is the most comprehensive observed quasar spectra to date. So in this work, we selected our dataset from DR16 quasar. And this catalog contains more than 750 quasar in the automated redshift range between 0 to 7.1. The SDSS Digital Sky Survey is a major multispectral imaging and spectroscopic redshift survey using a dedicated 2.5 meter wide-angle optical telescope at Apache Point Observatory in New Mexico. And according to the technical details of EBOS, the wavelength coverage is in range of 361 nanometer to 1014 nanometers. Information of quasars are collected in FITS-5, which are available in SDSS website. And in that catalog, the pipeline redshift estimation was reported. And but we have another automated redshift estimation methods that I want to explain it here. And the redshift of visually inspected estimation is the most accurate one, but it is really time consuming, and it needs a human expert to calculate the redshift. The SDSS pipeline redshift estimation is the result of principal component analysis performed on a sample of visually inspected quasars. This is the less accurate in this among these redshift estimation methods. Also. PCR redshift is also the result of a principal component analysis, but unlike pipeline redshift estimation, the reference sample has been carefully chosen to have an automated redshift corresponding to the location of the maximum of the AG2 emission line. Here we have a spectrum of a quasar at redshift equal to 0.65. And you can see the MG second here is among the prominent emission line. And this is the noise also. And various studies have shown that the MG2 emission line is a quasar broad emission line that is the best affected, that is the least affected by systematic shift. And in the bus spectral range, this feature is available in the redshift range between 0.3 to 2.5, which covers the most of our sample. Unfortunately, DR16Q catalog contains sources which are not quasar or not quasars at the given redshift due to the incorrect pipeline classification and redshift estimation, especially for quasars with redshift greater than 4. For example, in a recent research for undeclared quasar have shown the 81 entiries in DR16 that can influence our result. To tackle this problem, we set some restriction on our data selection. So we constrain our data only on the spectra of quasars with human expert visually inspected classification and redshift determination. The quasar in this sample are annotated with the class ID equal to 3, and as well as BAL, a broadband absorption line quasar with class ID 30, and Blazer with class ID 50, and also that's 81 non-quasar identified with this article. And the objects selected by ancillary programs are excluded from our data set. Under this condition, the data set which we used for training our CNN is composed of 231,000 visually inspected quasar, and here we have the distribution of the redshift in this histogram, and the pipeline classification and the visually inspected quasars are shown in this histogram. The difference shows that for redshift greater than 4, the objects of the catalog are not here. There is obvious differences between these two redshift reported. And this difference is due to incorrect pipeline classification and redshift estimation. As we all know, data preprocessing plays an important role to provide an understandable input for deep learning networks. And as an astronomical object, a spectrum is similar to time series, where each data point presents wavelength versus flux. Each raw spectrum in DR16Q contains nearly 4,050 100 flux pixels, which are uniformly situated in the range of wavelength, as I said, in the CSS wavelength range, 361 nanometer to 1014 nanometer. As a first step of our data preprocessing, we reduce them to 2000 pixels in the same range of the wavelength in order to have smooth input pixels. And at second step, the new fluxes are normalized via zero mean normalization method for the sake of improving the speed and accuracy of processing. And we collect this reduced normalized fluxes in the matrix, which n is the number of quasar and m are the number of pixels. And also normalized redshift is also applied as a labels, which is similarly stored in the n×1 matrix, which n is the number of quasar. The aim of deep learning and machine learning is to recognize all available characteristics and patterns in data, which helps in turn to solve unseen problems. The redshift or any physical characteristic of the distance source can be estimated by utilizing deep learning network, recognizing a deep pattern hidden in data. Some of these patterns probably are unknown or inapplicable by the traditional methods or even understanding by human being. The deep learning method in this research is dedicated to train a convolutional neural network. CNN have been used widely for machine learning tasks, and they have shown considerable improvement in both computer vision and time series problems. As you can see, the FNet architecture, we use the one convolutional one-dimensional convolutional neural network to learn a higher order feature from inputs and then try to predict the redshift of quasars. And the first layer here, the input layer, we apply the reduced normalized fluxes as input, and the filters of any convolutional layer slide along each flux and extract the prominent feature from the raw input dataset, as it can be seen in this figure. After every convolutional layer, we have pooling. We use the max pooling in order to reducing the dimensions and also concerning on the most relevant feature. The innovation of CNN is the ability to automatically learn a large number of filters in parallel specific to a training data set under the constraint of a specific predictive modeling problem.
A moment, Fatima. 5 minutes, okay? Your time is limited. Thank you.
Okay, thank you.
Okay.
The convolutional layer are initialized by HE normal initializer, and also ReLU activation function that is used allow the model to access the nonlinear modes if they are needed. And finally, we have fully connected feed-forward layer, connect the extracted feature to the output layer to predict the redshift. All free parameters in the model change progressively as our algorithm finds the best solution achieved with the backpropagation learning algorithm. As a hyperparameter optimization, we consider the number and the length of the filters of convolutional layers, and the number of nodes in fully connected layers, and the kernel size of the max pooling, and also we have adaptive learning rate and for a loss function, we use the mean squared error and Adam optimizer to optimize the loss function. We have QuasarNet as a former convolutional neural network try to predict the redshift. They are trying to find the local emission lines as you can see here, Lyman alpha and another prominent emission line that have used in traditional ways for redshift estimation. And we have the comparison between FNet and QuasarNet, these are the prediction, and the accuracy are almost the same, and we have to pay attention that QuasarNet are trained on more than 250,000 samples to train, but we use 60,000 samples for training set. And the differences between QuasarNet and FNet here is we mask the prominent emission line, and here you can see the spectrum, and this colorful band show the wavelength that we mask in our data set. And here our accuracy, we have 99.5% accuracy for velocity difference less than 6,000 kilometers per second. Deep learning, especially CNN, is a promising in future astrophysical studies. CNN can be utilized owning its several convolutional and fully connected layers to find the common deep hidden patterns in the spectrum flux in provision for improving our astrophysical knowledge of distant objects. Having the accurate redshift of quasar in hand, especially the high redshift one, helps us to modify our current knowledge of the cosmology, which in turn affects all areas of high energy astrophysics. Thank you for your attention.
Okay, thank you.
I think if anyone has questions, he may type the questions in the chatting box. Then the speaker could answer after his talk.
Okay. So let's, if there is no question, let's go to the next speaker, Aydin Momtaz. The title of his talk is Estimating the Photometric Redshift of Galaxies Using Regression Techniques.
Do you have my screen?
Yes, I can see you on your screen.
Yes. May I start?
Sure.
Greetings all. This is Aydin Momtaz representing a research collaboration among Mr. Salimi, Dr. Shakiri from Department of Physics, Isfahan University of Technology. We are really honored to participate in the 16th Marcel Grossman Conference. We are going to talk about estimating photometric redshifts of galaxies using regression techniques. First, let's have an overview over the topics we are going to discuss. In the introduction, we are going to speak about our motivation of the research, two main methods of spectroscopic and photometric redshifts, and some fundamental theories of machine learning. Then we are going to talk about our literature survey and the recent researches in this particular area and our methodology, and at last, our results and discussion. First, to begin with, I should talk about one of the most sophisticated astronomical surveys in modern astronomy, the Sloan Digital Sky Survey, or SDSS. It has been working for more than 20 years to make a map of the universe. Measurements of larger scale structure in SDSS maps of galaxies, quasars, and intergalactic gas have had a huge impact for test of the standard cosmological model that describes our understanding of the history and of course the future of the universe. Let's have a review over the details about many of the topics SDSS will address. We have galactic archaeology, the gas in the galaxy, which we mean the energy exchange between interstellar and gas and stars. SDSS will classify and identify roughly 100,000 star-forming regions and white dwarfs. And of course, multi-star and planetary systems. SDSS will measure the environmental dependence of the multi-star fraction in the disk and stellar clusters. SDSS have had many data releases, and we are using the last one, data release 16. It started on August 2018. It included both spectroscopic and photometric datasets, including infrared spectra, extragalactic spectra, integral field spectra for nearby galaxies. There were approximately 5 million useful spectra in the dataset, and 3 million of them were galaxies, and nearly 1 million of them were quasi-stellar objects. To begin analyzing our dataset, we should know how to measure redshift from both spectroscopy and photometric. Let's have a quick review over them. We all know that hydrogen is the most abundant element in the universe, and it is often seen in the galaxies. This spectrum comes from a galaxy. It shows strong emission lines. The hydrogen lines are already identified. The tallest peak, for example, is H alpha. The spectrum of such a region shows a pattern called the Balmer series of lines in emission. Now we should measure the shift of any one of those lines with respect to its expected wavelength. as measured in a laboratory on Earth. For example, the middle one is the expected spectrum of a hydrogen in a laboratory, and whether you measure the top spectrum or the bottom spectrum, you can say the galaxy has redshifted or blue shifted. Okay, now let's go to talk about our measuring redshift from photometric. We will be using flux magnitudes from the SDSS catalog to create color indices. Flux magnitudes are the total flux or light received in 5 frequency bands U, G, R, I, and Z. The astronomical color is the difference between the magnitudes of 2 filters, for example, UG or IZ. This index is one way to characterize the colors of galaxies. For example, if the UG index is high, as you see in the diagram, then the object is brighter in ultraviolet frequencies than it is in visible green frequencies. Color indices act as an approximation for the spectrum of objects and are useful for classifying stars into different types. If you want to measure the exact amount of one of the filters, magnitude of one of the filters, you can use this formula where F is filter transmission, S is the flux at wavelength lambda, and the constant mref encodes the calibration of the telescope. Okay, we've discussed so far that SDSS has observed millions of galaxies. It is relatively straightforward for a person with the help of a computer to measure redshift from a galaxy with an observed spectrum, as we saw earlier. But many galaxies have not been observed spectroscopically, we only have images. In addition, the large number of galaxies in these surveys makes this task nearly impractical to do by hand. We are going to use machine learning to calculate the redshift of galaxies from their measured colors. This task is ideal for machine learning, and there has been a substantial amount of research in this area, as you know. We have used 2 main regression algorithms, decision tree and random forest. First, decision trees are basically an ensemble of branching operating systems. They map a set of input features to their corresponding output target, and random forests are an ensemble of decision trees where they classify, where they are used for classification, regression, and other tasks. Okay, let's review over a quick example of how decision trees work. In this example, each node represents a decision that the robot needs to make to reach a final decision. In this example, the decision tree will be passed a set of input features, for example, outlook, humidity, and wind, and will return an output of whether to play or not. And here is our random forest, and they are basically made of several decision trees, and each tree votes by predicting target class, and then we use these votes for our final prediction. To have a more precise look over the algorithm behind decision trees, we can say that it splits the dataset to particular areas and allocates a value to each one of them. When an unknown datum is received, the algorithm investigates that this specific datum belongs to which of these areas and will allocate a target value to that datum. One of the early researchers in this area was from Firth et al. When they constructed an artificial neural network with a sample size of 20,000 galaxies and a testing set of 7,000 galaxies. They reached the accuracy of 0.023 for their AGN, which was a promising result in the year 23. And then some attempts have been continued in this particular area. You are seeing the accuracy of all of these researchers shown by delta Z norm. They have used local linear regression and mostly random forest. Some of them have used large training data sets, which really helps for the accuracy of the final results. And you are seeing our work that we're going to discuss the results in the final section. Let's begin our quest for the data analysis of the SDSS. Here, you're seeing the data pre-processing. There is a particular redshift allocated to each group of filters, UG, RIZ. And you are seeing the picture of the camera of SDSS where it takes the images of galaxies using these filter bands. Okay, now we have plotted a contour map of the results. It shows that we get reasonably well-defined regions where redshifts are similar. As you see in the picture, in some particular area, they are red, orange, yellow, and nearly white. It shows the value of the redshift. If we were to make a contour map of the redshifts in the color index versus color index space, as we did here, we would be able to get an estimate of the redshift for new data points based on a combination of their color indices. So we are concluding that color indices are appropriate features for a machine learning algorithm and where they can operate well enough. Here you are seeing the distribution of the dataset containing galaxies and quasars. You are seeing that the most of them are distributed between 0 and 3. Let's have a detailed overview of our decision tree. We can see how our calculated color indices are input as features at the top, and through a series of decision nodes, a target redshift value is reached and output. So here was our algorithm. And here is our optimizing process for our decision tree. We have plotted the maximum tree depth against the median difference of the predicted redshifts and the true redshifts. You are seeing that around maximum tree depth 19, we have our best results of the median difference. So the optimum tree depth was achieved through this criteria. This process was due to checking the overfitting, and we would like to examine how our decision tree performs for different tree depths. Specifically, we would like to see how it performs on test data compared to the data that was used to train it. However, as the model overfits with a difference in its accuracy on the training data and the more general testing data. Here you are seeing the effect of our training set size. You are seeing that we were able to have nearly 500,000 of SDSS data and exactly 400,000 of them were used for training. And at last, we reached the median difference of 0.017. Here is the final result of our decision tree algorithm. We can compare the predictions to their corresponding target values later when calculating the median difference and plotting the predicted values against actual values. Here, the color bar shows the density of the galaxies. So you're seeing the measured redshifts. When it is near 0, we have more dense distribution, and they are, and we expect the pattern to be nearly a straight line as you see in the diagram. Let's go to our random forest algorithm. As I discussed before, they are basically several decision trees. Each of the decision trees gives us a target value, and by having a mean over all the targets, we can have our final result as the output of the decision as the random forest algorithm. Here you are witnessing the final result of random forest algorithm. When the predicted redshift tends to be equal to the measured redshift, we are expecting to have a straight line. As you see, most of the data are distributed in a straight line with an angle of 45 degrees. So it gives us rather promising results as well. And here is our optimization process for our random forest. We had a grid search on the random forest algorithm. We reached the maximum tree number 600, and we've made the analysis over the maximum tree depth. As you are seeing in the diagram, near the tree depth 25, we have the minimum of the median difference, which we which we need the median difference to be as minimum as possible. So the random forest optimization parameters were number of trees were 600 and the maximum tree depth was near 25. Let's have a review over our final results. We are seeing that the mean accuracy of our random forest was far more better than decision tree, nearly 13%. The median difference is actually lower by 1/1000. And you are seeing the optimization parameters. Max depth was 25 for random forest, 19 for decision tree. Number of trees were 600 for random forest. Although random forest algorithms are a little slower on the operating speed, but they are way more better in all the categories as you see in the table. And you are seeing our delta Z norm, which is a criteria which we can compare to other similar researches, that it is 0.001. And let's review again the similar researches in this area where they use random forest algorithms. You are witnessing that we have reached to a acceptable delta Z norm with much lower training set size. And so we think that it can be, we think that it is an acceptable result. And in future attempts, we are going to separate the different redshifts of different objects in the data sets. And we are hoping to get promising results as well. Here are our references. And that's it. Thank you very much.
Okay, thank you. Any question? We have some minutes for questions. Okay, if there is no question, I have one comment on the way that you report the accuracy. This way that you report the accuracy delta Z of the average of delta Z, it seems that not be a good way to judge. I suggest that you use this velocity difference as has been reported in also in delta release of 16 of SDSS. There you can have a better understanding how your data are distributed around the zero. But this one, it's a bit hard to judge. So if you can, for your future reports, you can add also that.
Yes, of course. Thanks for the comments.
Okay. Okay, the next, thank you for the speaker. And the next speaker would be Dr. Beheshti Pur. The title is Deep Learning to Cluster Continuous Gravitational Wave Candidates in Broad Searches.
Thank you. I think ID needs to stop sharing so that I would be able to share.
Aydin, would you please stop sharing your screen?
Okay, great.
Okay, perfect.
Right. So hi, everyone. Thank you for having me here. I'm going to talk about the way that we use deep learning in order to search for continuous gravitational wave. And it's basically based on the two papers that we have published. So for more details, please look up these two papers. So in this talk, I'm going to first start about a general information about the continuous continuous gravitational wave. Then I'll talk about the clustering method, which is an important method which is used to do these searches. And then I'll talk about the deep learning network that we have used and the results. So continuous gravitational wave is a type of gravitational wave which has not yet been detected due to its weak signal amplitude. It's expected to be emitted from compact objects with some non-axis symmetric deformations. For example, when we have a neutron star with a mountain on top, it could emit continuous gravitational wave. And since it's emitting continuously from the source, that's why it's called continuous wave. And there are two types of search for continuous gravitational wave. One is the targeted search, which we actually know the information of the source. We know where it's located in the sky, and then we have information of the frequency. And so it makes the search to be much simpler. While there is another type of search, all sky search, which we have no information about the source, and this is actually the type of search that we are interested in, which makes the search more complex since we don't have any information of the source. So we have to go through all the combinations of frequency derivatives, and the sky position to find any gravitational wave that could emit from this source which we don't know. So now, let me talk about a value that's very important when we are searching for a gravitational wave in general. It's called detection statistic, that we calculate this detection statistic, which is a likelihood of having a signal in a specific template. So when there is a loud signal or a disturbance in the data, it actually raises the detection statistic to be above the noise level. So let's say we have let's for as an example see in the image here, it's showing a 50 millihertz band of the data. It shows the detection statistic as a function of frequency and spin down. And then there has been some fake signals which has been injected to this data. So you can see this overdensity of the points that are raised above the detection statistic due to this signal. And so instead of like having just one point being raised, there is a plethora of points, like a hill that's happened nearby the signal. So what the clustering method says is that let's bundle together all these raised points that happens due to the signal, and bundles them together and use these as a to do any follow-up searches to find continuous gravitational wave, instead of looking into the whole data, which makes it more complex. So in this case, the clustering actually makes us dealing with a simpler data and also actually less computationally intensive. But the problem is that the morphology of these overdensity regions, which we call them clusters, the morphology of these clusters depend on the amplitude of the signal, the type of the data, the type of the search setup that we have. So this makes the clustering method being a lengthy process to tune for all of these things. So this brings the idea that what if we can use a neural network in order to do this clustering for us automatically without doing any of these fine tunings. So so let's now look at the type of the data that we have and what exactly we are looking for. So we are having the data from LIGO observation. We give this data to Einstein at Home Computing Service, which actually this is the place that all the detection statistics are calculated, and then the results outside of the Einstein at Home would be the value of the detection statistic as a function of the frequency derivative, and the sky location. And now we are making a small simplification. We only look at the 2 dimension of frequency and frequency derivative and assign our data to an image, to a 2D image, with the height and width being the frequency and spin down, and then the value of the detection statistic being the pixel values in here. And then we actually somehow project the sky location onto this plane. And since we need to have some clusters into our data, we need to add some fake signals into the data so we can see some overdensities, some clusters. So here's an example here. This is going to be an example of the 2D image that's going to be used. And the type of the work that the network has to do is finding these over density region, these high intensity regions for us in that image. So now that we know about what we want the network to do, let's talk about the network that we have used, which is the mask RCNN network. It's a type of an instant segmentation network, which does actually what exactly we're looking for. It looks into an image and extract the features that you're interested in. In our case, it's clusters, and then find the regions which has the more probability of including the clusters, and then put a boundary box around it. And then in these box, it classifies the object, and as an output gives us all the pixels which are included in the clusters, which is exactly what we are looking for. So now that we know about the network, let's see how we prepared our training set. As I mentioned, we have the LIGO data and we add some fake signals, and we created the images that we are interested. But the images that we have are too large. It has on average about 10 to the 9 pixels, which is impossible to be given to the network. So the trick that we're using here is that we divide the clusters that we have into the 2 types, the larger clusters, which are generated using from the loud signals, and the smaller clusters, which are created by the weaker signals. So for the larger clusters, we downgrade the resolution of the image by averaging over nearby pixels. But for a smaller cluster, we keep the high resolution image. So here, as an example, you see a large cluster, which is in a low resolution image, and you still can see the cluster and its shape. While here you're seeing a weak signal cluster, which is in the high resolution image now, but if we downgrade the resolution, it won't be possible to see this type of clusters in the lower resolution image. That's why we keep those in the high resolution. And even by using this trick, we are dealing with a large image. And what we do now is we tile up the image into the smaller sizes that can be handled by the GPU memory that we have available. We have the 32 gigabyte GPU memory, so we tile up it in order to be able to give into that to the GPU. And since we're dealing with a supervised network, we need to prepare the ground truth for the training set. And to do that, we use a graphical software and an iPad with an Apple Pencil, and we actually mark through the regions that includes the cluster, and then save those regions, transform it into a binary matrix, a ground truth binary matrix that can be used later on in the network. Okay. There it is. Okay. So now now we have 2 sets of data: a data which including louder signals, and the data which including weaker signals, and we train the network on each of these sets separately. And then we are ended up with 2 trained network, and we use them in cascade at the end on the data. So we first apply the network which is trained on the louder signals and let it find all the clusters that it can. And then we remove those clusters that has been found by this network, and then the rest of the data is given to the network that was trained on the weaker signals and let it find the weaker signals on those data. And here is an example of the output image that we will have. There are 3 clusters here, and the blue line showing the ground truth that we have picked, and the red line showing the one that the network found for us. And let me show you the results of the detection efficiency of this network. Here on the left, I'm showing the contribution of each of the trained the network that are trained on the weak signal and the louder signal, and then the yellow showing the overall detection efficiency, which, as you can see, there is about more than 95% detection efficiency for the signal amplitudes above 0.018. And here I'm comparing the detection efficiency of our cascade network with the most recent deterministic clustering method in the paper that has been published in this paper. And as you can see, our clustering network has an excellent performance on, our cascade network has an excellent performance on the lower signal amplitudes, which are actually the signal amplitude of our interest. The continuous gravitational wave is mostly expected to have these type of signal strength. And also, a false alarm rate is also a very important factor for us. Having a lower false alarm rate would actually lower the computational cost for the follow-up searches. So here I'm comparing the false alarm rate of the cascade network with the clustering method. And as you can see, in overall frequency ranges that we have, in overall, the cascade network had about half the frequency, half the false alarm rate that the clustering method has. And if you're interested to know why in this region we have a larger false alarm rate compared to the other regions, is because of the lower training set that we have in this range of the frequency, which makes the poor network to not being completely trained on this range of the frequency. And that's why we have this larger false alarm rate in this region. And with that, I put up my summary here. So we implemented a mask RCNN network to identify signal clusters to search for continuous gravitational wave. We trained 2 networks, one on the louder signals and one on the weaker signals, and showed that the combination of these 2 networks has an excellent performance compared to the clustering method at lower signal amplitudes. And please look into the 2 papers that we have published for more details. And I will be happy to take any question now. Thank you.
Okay, thank you for your interesting presentation. Any question? Okay, so if there is no question, we can thank you again. Go to the next presentation. Polina Valadikina. The title is On Parameters of Fractal Distribution of Relic Wormholes.
Hello.
Yes, we can hear you.
Mm-hmm. 1 second. Sorry. So, hi everyone. My name is Vladikina Polina, and I will introduce you my presentation, Possible Effects of Fractal Distribution of Wormholes. So, The nature of dark matter presents one of the most challenging problems of modern astrophysics, and particle physics offers many possible variants of this view. The most promising are weakly interacting massive particles, which can be like new particles beyond the scope of the standard model, and particles composed of already known, for example, complexes of neutrons and even primary neutron stars. However, unfortunately, such particles do not solve the problem of dark matter. The experiments at the Large Hadron Collider do not show the presence of particles escaping beyond the standard model. And moreover, such particles should have some exotic properties. An important feature is that in the early universe, in the moment of recombination, such particles should have a rather high density, but in this case do not interact with baryons or radiation. Otherwise, they would cause too strong fluctuation in the temperature of the relict, and such a possibility is excluded by the observed power of the entropy spectrum. Another important feature is that in the modern universe, in centers of galaxies, dark matter particles have much more modest densities, but they should possess a sufficiently strong interaction with baryons to form the observed core distribution of dark matter. We recall that numerical investigation based on DM particles predict the presence of a cusp in center of galaxies, which is the consequence of the potential nature of initial velocities and the fact that DM particles interact via gravity only. One of the possible solutions to the problem is based on the fact that local topology of space may possess a rather complex or fractal structure. In our opinion, fractal topology provides the only natural explanation for such relationships. The origin of fractal topological structure is directly related to predictions of lattice models of quantum gravity. Lattice models predict that on Planck scale, space-time has something like a Fermi structure that has fractal properties and present in a two-dimensional representation, something similar to the Sierpinski carpet. On the next slide, we can observe a three-dimensional distribution of a sequence of galaxies where a cut was made every 10 megaparsec. It resembles as a Menger sponge. On a very small scale, space-time form can be described by the distribution virtual wormholes. On a laboratory scale, the vacuum is stable, which means that all virtual wormholes appear and disappear irrevocably. However, if we put that the early universe experienced an inflationary phase, we can expect that exponential expansion will extend all scales very quickly, and some virtual wormholes will not disintegrate. Actually, they form the initial condition of the topological structure of space. In the open Friedman model, a set of stable wormholes can be constructed by factorization of a space by a discrete subgroup of a group of motions for the space Lobachevsky. The simplest wormhole here has a throat in the form of torus. Such wormholes expand into space consistent with the expansion of space. But that doesn't mean they can collapse. In particular, the development of density perturbation can lead to the collapse of an entire area of space. But the mathematics of toroidal wormholes will allow the universe to have complex topological structure. So I will describe the factorization scheme we have here. To begin with, consider the open Friedman model where the spatial matrix corresponds to the Lobachevsky space. Using the following coordinate transformation, we get the implementation of the section in the form of the upper complex half plane, which is the Klein model of the two-dimensional Lobachevsky plane. And consider two geodesic lines in the plane that corresponds to both semicircles. The factorization means that any 2 points of the plane represents the same point if they are connected by the next relation. The above factorization corresponds to the cut along two geodesic lines and subsequent gluing along them. The resulting space is a wormhole which connects two independent Lobachevsky planes. In comparison to the ordinary Lobachevsky space, the space with wormholes represents a space with a specific factorization. For example, in flat space, the factorization over translation in one of the direction gives the cylindrical space, and one of the coordinates becomes a periodic one. This means that corresponding modes are classified by discrete wave numbers instead of continuous ones, and therefore some modes are absent. Analogously, the factorization of the open model selects only a particular solution among all possible solutions for the unrestricted space. Therefore, from qualitative and quantitative standpoints, the evolution of perturbation will show essential deviation from the behavior in standard Friedman models. Analogous deviation are indeed observed and are interpreted as a presence of dark matter and modification on general relativity. So take into account the simplest model we obtained in previous works, which explicitly demonstrate that non-trivial topology can model the effects of dark matter. The model is based on spherical wormholes, while actual stable wormholes, as I said before, should have a torus-like throats. We assume that throats are averaged over orientation, then the spherical symmetry restores, and such wormholes can be considered in the leading order as spherical ones. In the case of weak gravitational fields and potential perturbation, Einstein equation reduced to the Laplace equation for Newton's potential. The behavior of perturbation is determined by the green function, but in the presence of wormholes, it changed. It is convenient to describe corrections which appear due to wormholes by the presence of additional sources, fixture sources. So we may think that the space remains Euclidean, while proper periodic conditional throats are accounted for by the bias of sources. Here, the bias function describes corrections to Newton's law, which appear due to the non-trivial topology of space. In the equation, the parameters alpha relate to the Hausdorff dimension of space D, and it characterizes the fractal structure itself. So the value of the parameter L may somewhat change from a galaxy to a galaxy that reflects the presence of the initial inhomogeneity of the metric at the moment of recombination. The empirical Green's function that we constructed from the analysis of rotation curves in galaxies allows us to directly limit some parameters of the fractal distribution. So in the end, the bias in this form and the homogeneity of total matter, baryon plus dark matter components, lead us to the origin of Tully-Fisher and Faber-Jackson relations. Therefore, this can be considered an indirect indication of the fractal topological structure of universe. So in the article, Unexpected Circular Radio Object at High Galactic Latitude, the scientists found a way to identify circular features in space, ORCs, which can represent various space objects, and according to our assumption, wormholes. So moving in that direction is a non-trivial yet unexplored task. In future works, we plan to apply the findings and results to the search for more complex structures. It is planned to use machine learning and computer vision to find them, and we will be glad to hear suggestions for work in this direction. Thank you for your attention.
Okay, it's very interesting to integrate the wormhole with the machine learning. First time I've been watching such a talk. So any questions or comments? If not, we move to the next speaker. So who will be the next one? So next.
Hi, no, I think it's me, if I'm not mistaken.
Oh, yes, I can see you.
So let me try to share my screen. Sorry, I think this is this one. Can you see the screen?
Yeah, I can see your screen now.
Okay, okay. So this is the first slide normally, and if it's okay, I'm going to start.
Yeah, okay.
Okay. So first, thanks for the organizer for letting me discuss my work. Actually, our work is the work of our PhD student with Marion and Mo, and which
It's not on full screen.
Oh, sorry, but I tried to be on full screen, but I don't know, because to me it is. Maybe I can do like this. Is it better?
Yes.
Okay. So I will present the work of Marion Elmo, which is our PhD student with Nabila again that you just heard. Hi, Nabila. And it's about encoding large-scale cosmological structures with generative adversarial networks. So I will try to explain how we make the use of, I don't know if you know, it is a famous neural network that's called GAN that has been very fashionable these last years, and how we use it to, let's say, catch the density of matter distribution that we can observe nowadays. Okay, so it's a bit hard like this, but maybe you can unzoom a bit for me. Okay. So just a little bit of a reminder, even though we probably all know about this, but yeah. So about the cosmic web and large-scale structures. So at the beginning of, well, not at the beginning of time, so many years ago, when the redshift was only z equal 10, the matter was almost homogeneous, and we didn't see anything interesting appearing in this distribution of matter. And through the evolution of the gravitational interactions, or what's called gravitational collapse, the voids are getting larger, and the overdensity are getting more and more overdensed, until structural form through gravitational collapse. So what we can see, for instance, up to nowadays, so redshift c equals 0, is that we have a very complex pattern of matter distributions with very big halos and very large voids. So these images are taken from the illustrated simulation that we mentioned a little bit later. Now, if we just look at a snapshot of this exactly this matter density nowadays, this is the kind of complex distribution that we observed. Actually, this is a distribution, but we also obviously observed it in the sky. So we have a series of very dense regions that we call halos that are here, for instance. They are very, very dense. They are a cluster of a galaxy, for instance. And they are somehow linked, if you wish, or they are like, or there is like this kind of web representations that are connecting these halos between themselves, and that we call filaments. So they contain galaxy and diffuse gas. So this is like this, for instance, between those two halos, you can see there's a very nice filament here. They are not so easy to observe, but they're there. And in between these filament and halos, you have also large empty regions that we call voids. So they are largely not as dense as the other two ones. So again, this is a snapshot from the illustrated simulation. So, okay, so the interesting part is that to study the evolution of the gravitational collapse is very difficult, because obviously you have a lot of nonlinear effect going through, and therefore we're doomed, at least at some point, to use a numerical simulation, because linear, let's say linear approximation are kind of not working at some point, and nonlinear computation are very difficult. But yet the problem with simulation is that even though they are an essential tool to compute the nonlinear structuration of matter, they take a very long time to perform. For typical n-body simulations, where you have 10 to the 6, 10 to the 10 particles, so we can take those two examples. For instance, the Millennium simulation, which take 250,000 CPU hours, so 28 days run times, and more complex one like the hydrodynamical illustrated simulation with 19 million CPU hours, which run for 3 months. So the thing is that obviously with this kind of simulation, you cannot just wake up in the morning and decide that you want to run one, because it will take a lot of time. And we will see at first a way where using generative adversarial model to somehow bypass these kind of things. It's not totally true, because you need to have some data at first, but we will see how once we learn this kind of distribution, we can do interesting science with it. Okay. So the goal now that I will present in this presentation is first, can we use machine learning to reproduce statistically similar images as the one I show you? Because of course we can have many of them since the universe is very big, using deep learning methods. And a second question that we ask ourselves is, can we make further use of the trained network? Because obviously, if it's just reproducing what we already simulated, it would not be as exciting as this. But we will show you that once we train this network, we can make use of them because they have learned interesting statistical property about this the cosmic web. So let me try to remind you what are GANs, so generative adversarial networks. Very, very briefly, I will refer to the paper of Goodfellow who invented it for people interested. So GAN is what we call generative models, in the sense that it takes a bunch of data sets, so for instance, pictures of the illustrated simulations, and it tries to reproduce the same kind of images or boxes of particle distributions with sharing the same statistical properties, hopefully. The way it does that is the following. It's very interesting, actually. It uses two distinct neural networks. First, you have one neural network that we call the generator. And the generator is what will try to create a statistically similar data as the dataset. So the generator works as follows. It takes as input random vector x of a given size, let's say 100 Gaussian identically distributed and independent variables. And from it, through a transformation that I call f, which dependent parameter θ1, it creates a fake image, or in the case of illustrators, a fake distribution of matter. A fake in the sense it not from the true dataset. Then you have the of course, if you don't, well, at the beginning you didn't learn the network, so you don't do anything, and I will tell you how to learn this. And you have a second neural network that we call the discriminator. The discriminator takes as input an images, or in our case, matter density, such as the illustrated dataset or one that has been created by the generator, and it tries to estimate the probability with which it believes this data is from the true training set for the illustrated dataset, for instance, if it was from illustrates, rather than generated by the generator. And this is yet another neural network that I call G, which depends on parameter θ2. Now that we have those two networks, the interesting part is how you train them. And to train them, actually what you do is first, you will generate a fake data. So you take a random vector x, you compute its artificial data f of x, and then you will ask the discriminator, does this fake data is from the true dataset or from the generated dataset? And what you will actually do is we try to fool the discriminator. You will try to say to the discriminator, this you want the discriminator to mistaken and to believe that it is from the true dataset. So you will adjust the weight θ1 of the generator to adjust the best the images that is created, such that the discriminator is mistaken. And as a second point of view, you have to train the discriminator, otherwise it will be too easy. And with the discriminator, you will give him either true data or generated data, and you will give him true answer. So this is a true data, or this is a generated data, and you will train the discriminator to recognize true from false. So on one side, you ask the generator to improve itself such that the discriminator gets wrong, and in the second step, you train the discriminator to recognize better and better true data from fake ones. And from it, you can write these losses that I will not enter into more detail right now. So this is the machine that we would use to learn the matter distributions of the our matter coming from using dataset from simulation. So which kind of dataset we use? Well, actually, we did on many cases, but let me describe you what we did on a few several cases. So we have, let's say, a one which was used because it takes as input images, which was easier for us. So from a slice of matter distribution, a cube, let's say, you will slice this like this, as in all directions, basically, and then you will project along the z-axis to get matter distribution that you can put under the form of an image. And since if you do that, the halo will take all the signal. You take the log, and you smooth it nicely, and you get from the dataset you get these nice halos and filaments that you can observe. So you take this is the images that come from the dataset that we use. It was not illustrated, actually, it was a gadget simulation. But we also did a true 3D case. So in the 3D case, you take the boxes and you do nothing. So this is just a slide that I take, but actually we worked with boxes. It's just to show you that we take the box and then we project some slides to look at it, and but really we feed the neural network with boxes and we see the same thing. And we are also native to this simulation that I might show at the end, but because you can simulate the evolution of the universe into the universe, but I will just mention it briefly maybe at the end. Okay, so now we trained our model and we have this both set of images, and I dare you to recognize, so there is a separation here, which one from the left part of the right part are coming from the gadget simulations, so the one we use for training the machine, or from the generative model that has been generated by our machine learning model. So hopefully you are not able to distinguish. Maybe I never managed to do it, so I think you cannot. But if you can, just send me an email. Okay, so this seems to tell us that at least by visual inspection it works, but we wanted to be sure, so yes, okay, true on left and fake on right. So we wanted to be sure, so we start to dig statistical properties of these images. So of course we compute the power spectrums first, and you see that if you look at the power spectrum of both the one from gadget in red and the one that has been generated by our model, they are almost perfect for many scale of pixel density value. There is just a small glitch at the beginning, which is a kind of not very clear why, but okay, at least for many order of magnitude, it's almost perfect. Now we can also look at the mean particle density distribution. So we see again that this is a complete agreement in both cases. Yeah, sorry, this is the pixel PDF and the power spectrum is below. The Bohr spectrum is this one and it's almost perfect. And the pixel density PDF has some glitch here. Sorry, it's very early to me. And finally, with the peak count, so peak count is just counting if you have one pixel that is brighter than all its neighbors, you count it as a peak and you add it in a histogram, and you do it for both the generated set of images and the simulated images. And we see again that this statistic is reproduced perfectly by the images generated by the GAN. So it seems that in that case, at least, the GAN is perfectly reproducing these four statistical properties. Of course, we can make it better, but by visual inspection and this statistical property, it seems that we have a nice reproduction of the matter density. Okay, so now that we are convinced that the GAN is able to do that, we want to dig a little bit, what can we do with this machine? So just to show you one type of, let's say, toy application that we did, making use of what we call the latent representation. So in the GAN, that is pictured here, you remember that we have this random noise here that are generated the images. What we can do is make what we call an autoencoder. So autoencoder is usually a machine that takes as input data, try to compress it into what we call a latent code, and then decompress it in some sense or decode it. And we hope that the input and the output are similar. So if you try to make autoencoder with directly with images, usually it's not working. But in our case, since we have this generator that already generates very beautiful images, we can try to make use of it in order to improve the autoencoder. So what we did is that we take the generator part and we put it in that right place here, there, and the decoder part. This is the encoded vector that is here. And then we put an encoder here, and we use already the architecture of the discriminators, and it seems it was a reasonable architecture to make the work. So in that case, what we will do is that we'll take a true images that will go through this neural network that is actually has the form of the discriminator, but it's not a discriminator. And it will find an encoded vector of 100 dimensions in our case. And then this encoded vector through the decoder will normally generate an output which might or might not look like the true images. And then we will adjust the weight of the encoder in order that the decoded images should be as close as possible from the true images. So we have to say it a little bit more clearly, they have the input images, we encode it, we decode it, and we want the input and the output to be the same. And How we do that? We adjust the parameter of this red part here that we call discriminator, which is now an encoder, and in that sense it will learn the latent representation of this true image with respect to the generator of the GAN previously trained. Okay, so if we do that, we can try to quantify how well it works. So for instance, we take this first row of 5 images there, and after learning the autoencoder, and this is the output we get from the trained autoencoder. So this is how well it reconstructs the image that I give him as input. So it takes the image as input, it compresses it into its latent representation, and then it generates the images associated to the found latent representation. And this is the second column that you get. Now you see that it's very similar from one to the other. So what we can try to look is how well it is, so how much it is similar. And we see that if now we take the 20 most bright pixels and put it to 1 and the other we put it to 0, we can see that, at least in that case, from a very bright pixel, you recover very, very well the different structure at large scale and very, very dense structures. And then if you take the 40% and 60%, okay, 80% is not maybe not so used, but you see that you really recognize that you have the same large scale structure appearing in both images. Let us think that this worked quite nicely. Okay, so now we can also try to look at the overlap of structure taking those two images. So you see that in yellow you have the overlap, so it's quite a strong overlap between the two. And in green you have the when it's not overlapping. And we can quantify this overlap. So this is this yellow curve with respect to random images. So a random images will be the black one. This is the number of pixels you put to one with respect to that the threshold to 1, and you see that you have a very nice improvement with respect to random permutation of the pixel in that case. Okay, so to conclude on this part, what the message that I'm trying to convey here is that GAN are good alternative if you want fast generation of simulation like dataset. Of course, you need to first prepare the GAN and learn the GAN, but once you do it, generating a new cubes of matter density is just a matter of seconds. Second, we try to design statistical estimator to show that there were very good agreement between the input and output beyond visual inspection. So it is not just that it looks good; it's good according to these statistical estimators, and I think it's a good basis for future comparison. And finally, we show that this autoencoder using the generator can be used to produce further tools, such as, we just showed the one that it's able to auto-encode its own dataset. But when you have a smart latent encoding of your dataset, what you can help to do, for instance, is try to guess missing values of your dataset or improve or corrupt data, so on and so forth. And a further application of which we are working, and I think I have time to show you a little bit a showcase, is that you can try to infer density from Redshift. So for instance, let me just finish on this. You take the same autoencoder, but instead here of getting a true image at z equals 0 and recover image at z equals 0, what you can do is take a true image at a different z, greater than 0 then, and infer the image that results from the evolution at z equals 0 with these constructions. And actually we make some tests with, for instance, input snapshot at z equals 3. So we give the trained autoencoder a snapshot at z equals 3. This is the output that we should get because we have the evolution from the gadget simulations. And this is the output on the third line that is predicted by the autoencoder. And you see that it's giving quite incredible results in the sense that just starting from the first row, it is able to infer the last one, which is very close to what is the true output obtained from the numerical simulations. Thank you for your attention.
Okay, thank you. I have a question. Did you check, is there any connections between those noisy, those parameters, random parameters with the physical parameters?
Well, that's one of the problems with this big deep neural network, is that it's very complicated to correlate the learned parameters with physical parameters. And actually the GANs they are, at least the one we use, they are really not well designed to do that. So you might construct some more carefully, more carefully neural networks such that you can extract physical content, but this is not the case here.
Yeah, I see. I saw for your encoder you have 100
Yeah.
free parameters. Yes, maybe you can see some trend, not the real connection, but some trend.
Yeah, I guess the nice thing with this neural network is that you can really play with them because they have a lot of like different component that you can add them and you can play with the learning. So I think you can perfectly imagine procedure where you add some physical meaning that you want to impose to your model, such that later when you train your model, you can eventually open the black box, or at least a little bit, to see how well it is described in terms of physical quantity. But it's not so easy.
Yeah. See. Okay, thank you. Any other questions or comments? I see in the chat room. Hi, can you tell about other places where GAN can be applied? One question from the chat box.
You mean, I guess in cosmology, you mean like just, well, GAN can be used also. The fact is that if you want, there are the GAN we use is one of the most basic one, but you can also add what we call you can add more parameters such that it's able to distinguish. But for instance, you could add the parameter that is trying to infer the value of Z from your images or stuff like that. But it's true that I didn't really think about other use rather than in this type of cases right now. But as soon as you need to, let's say, if you need to model a complex probability distribution, it's usually a good tool to at least to catch it first, and then eventually make a more interesting use of it.
Okay. So we go to the next speaker. Okay.
Okay. Thank you.
Okay. Thank you. Thank you very much.
Hello. Can you hear me well?
Yes, I can hear you well. Please share your
Okay.
screen.
Sharing the screen.
Yeah,
Can
yeah,
you see
yeah.
the presentation?
Yeah, we can see.
Okay.
Okay. We can start now.
Okay, thank you. So, hello. My name is Miguel Conceição. I'm going to talk to you about the emulation of cosmological density fields and gravitational wave parameter inference using dimensionality reduction and supervised machine learning. I hope I can be as clear as possible and maybe provide you some insight. Currently, two of the major challenges in cosmology correspond to the understanding of the origin and growth of large-scale structure and the physics behind the progenitors of gravitational waves. These are two phenomena where gravity dominates at opposite scales and strength regimes. And in order to study such force, one usual approach is to perform simulations of mock data to be compared with the observations with the objective of constraining our theoretical notions. At the side of structure formation, this mock data usually comes in the form of n-body simulations. And with upcoming surveys like Euclid and LSST Vera Rubin, there is great urgency in generating large databases of this mock data. The problem is that, as mentioned before in previous presentation, these simulations take a huge amount of computational resources and time, and that poses a great bottleneck in research, and that's also where our work enters. We aim to relax that bottleneck by using machine learning tools to provide high accuracy emulations in a minimal amount of time. Similarly to the n-body scenario, current approaches for parameter inference from gravitational waveforms also rely on computationally heavy and sometimes model-dependent methods. And with detectors like LIGO and the upcoming LISA, there is also urgency in developing tools to efficiently extract information from this kind of data. So here we aim to generalize the n-body approach to provide fast and accurate inferences of astrophysical parameters concerning the progenitors of the waveforms. But what parameters we'll be considering in the case of n-body emulations, since our initial simulation dataset is composed of dark matter simulations, we'll be using the dark matter density in a first scenario as a single free parameter. Then in a second scenario, we'll be adding the redshift as a second free parameter in a two-dimensional improvement. For the gravitational wave case, since the chirp mass can be inferred from observations, we'll be using it as our parameter for inference. Now, but in order for you to understand the actual innovation behind our approach, we need to understand what the usual approach consists in. In this kind of regression problems, the usual approach consists in the direct application of supervised learning methods in raw data. In this branch of statistical learning, regression algorithms can be built from what we call training and test data, relating a set of independent variables in this data with a set of dependent variables for prediction. In our case, we'll be having n-body simulations and approximated waveforms. Using the training and the test data, the algorithms can progressively improve their learning until reaching a final converged model, which can be used in a new set of independent variables for prediction of the quantities of interest. Here we'll be using 4 different algorithms: the random forests, extremely randomized trees, neural networks, single layer ones, and support vector machines. But the actual catch behind our approach is that we do not provide the data in its raw form to the supervised learning methods. We first take advantage of the redundancy intrinsic in the data and transform it using a simple projection method already mentioned in a previous presentation called principal component analysis. This method takes our training data as an input and projects the observations into axes of maximal variance. Each vector of projection coefficients is called a principal component, and it will be these principal components that will serve as inputs to our supervised learning methods. In the case of gravitational wave inference, we'll be using them as independent variables used to predict the chirp masses, while in the case of n-body emulations, we'll be using them as dependent variables to be predicted given the mentioned cosmological parameters, and to consequently be deprojected into the original density field representation to be compared with the ground truth. Now, as measures of comparison with the ground truth, for the n-body case, we'll be using the power spectrum and the bispectrum, comparing our emulation with the simulation for the Planck cosmology. In the case of gravitational waves, we'll be using a simple root mean squared error to compare our inferences with 255 chirp masses in this range. Now, a quite lengthy and sometimes crucial aspect of our work consisted in the optimization of the supervised learning algorithms. Each of these algorithms is governed by a set of so-called hyperparameters, which define their structure and overall properties. So in principle, we could set these hyperparameters in a way that gives optimal results. So that's what we have done. We optimized a set of relevant hyperparameters mentioned here in this slide for each of the algorithms, using 3 different optimization schemes: a grid search, cross-validation, and bootstrap aggregating, ultimately choosing the one which gives us the best results. For the particular case of gravitational wave inference, since the principal components are used as dependent variables, we also optimize them using a simple grid search. Now let's get to the actual results, starting with the n-body emulations. Here I show you the main results for the single free parameter scenario, implemented with a data set at redshift 0. At your left, we can see the power spectrum curves in the top panels, while at your right, we can see the bispectrum curves for each of our 4 estimators against the ground truth in blue. The lower panels show a ratio of the estimated quantities against the simulated ones, the ground truth, for both the power spectrum and the bispectrum. Now, regarding the power spectrum results, the results were quite satisfying. We obtained an accuracy of 99% or higher in all of the K-domain using our best performing algorithm, which in this case was the single layer network. The remaining algorithms, as you can see, decrease their performances quite a bit in the large scale regime. And this could be, and this could be attributed to the lack of independent modes in our training data. For the bispectrum, we still managed to achieve percent level accuracies in about half of the theta domain using the neural networks or the random forests. But when we come down to really large thetas or low scales, if you want, the results decrease quite a bit. And this could be explained by the fact that lower scales depict highly nonlinear behavior, which is expected to be less predictable or compressible. Now, here are the results for our attempt to improve our method, adding the redshift as a second free parameter. Since we are under the so-called curse of dimensionality and we only managed to increase our data by a factor of 4, the quality of the results decreases a bit. Nevertheless, with support vector machines, we still managed to achieve a percent level accuracy in the central regions of the K-domain, which shows a clear advantage of this method in higher dimensional contexts. Now, regarding the bispectrum,
قبول نکرد. آقای دکتر تو عنوان سخنرانیش نوشته بالاش برای کدوم تاریخه که اون پس کد اون تاریخ رو استفاده کنیم.
I'm sorry, could you mute?
بله. نه آقای
So moving on, regarding the bispectrum, the results are not so good. The quality decreases to an accuracy of 85 to around 95% in most of the domain. And this could again be explained by the nonlinear nature of this quantity. Now, in another attempt to improve our method and explore less typical approaches, we performed a demonstration of functional principal component analysis in the single free parameter scenario. This is quite a promising method, in my opinion, because by combining the compression capabilities of PCA with the predictive power of the supervised learning methods, it enables us to shortcut the later. In a way, we bypass the need to apply the supervised learning step, making our pipeline more efficient. But such a powerful method comes with disadvantages, namely that it is memory heavy, and thus we only manage to apply it to a smaller data set of 64 cubed voxel simulations instead of 128, as in the previous case. Nevertheless, when compared with the previous best performing method, the neural networks, in the same data set, the results are quite good. For the power spectrum, we see that we achieved an higher stability here with FPCA in red and an higher accuracy, especially for the large scale regime. For the bispectrum, the differences are even more striking, where the FPCA achieved an higher accuracy for most of the theta domain and especially at the large theta regime. Now, traveling to the gravitational wave case, here I show you the main results for inferences from gravitational waveforms in frequency domain. The higher panels show the predicted chirp masses against the real ones, the ground truth, while the lower panels show again a measure of the ratio between both. From top left to bottom, we can see results concerning inferences from gravitational waveforms emitted at increasing distances. So we have decreasing signal to noise ratios up to 100 megaparsecs. And if you consider chirp masses above 14 solar masses, the results were quite good. We achieved accuracies above 98% with our best performing method, which in this case was the extremely randomized trees. But when we come down to really low signal to noise ratios, as expected, the results are not so good. Nevertheless, support vector machine manages to excel when others don't and achieves an accuracy of around 95% if we consider chip masses above 16 solar masses. And this is particularly impressive if we consider that we trained our algorithms on waveforms without noise, and we are testing them on noisy waveforms, which shows a high generalization capacity. Now, apart from the accuracy, our other main objective was an increase in the efficiency of the method. So here I show you the CPU runtimes for the n-body case. In the first row, we can see that in our single 3-parameter emulation scenario, we obtained total times below 0.8 seconds, while in the 2 3-parameter scenario, we obtained times below 4.5 seconds. These for both the principal component estimation and the consequent deprojection into the original density field. We consider this quite an achievement because it corresponds to a 3 order of magnitude improvement in the efficiency compared to a simulation of the same scale performed in the same system. Now, regarding the gravitational waves, the efficiency was also quite good. For the higher signal to noise ratio regime, we obtained total times below 0.2 seconds, while for the lower signal to noise ratio regime, we obtained times below 0.3 seconds. And keep in mind that this corresponds to the simultaneous projection and inference of 255 waveforms. Now, to conclude, here I make a wrap up of our work main contributions. We first managed to achieve state-of-the-art accuracy while using the simplest machine learning methods. We obtained multiple order of magnitude improvement in the efficiency of the methods, at least for the n-body case. We additionally implemented a successful demonstration of functional principal component analysis in a smaller data set, which is quite unusual in cosmological contexts. And finally, and most importantly, we came up with a highly generalizable framework because since we should be able to apply our methodology to any 3D scalar field, not only dark matter density, and to time domain and frequency domain data of different nature apart from gravitational waves. Thank you very much for your attention. I hope I can answer any question if you have them.
Thank you for your nice and clear presentation.
Thank you.
I have a question. In your slide number 12, you talk about this decreasing amount of data. Do you have any kind of intuition if we were able to increase the, I think number 12 it was?
12, this one?
Yes, because you have used, instead of 128, you have used.
All right, yes.
Yeah, this one, do you have any intuition if we were able to increase to 128, how it would affect our result?
Well, not exactly, because with my available resources, when I tried to increase the training data, the memory was not available, so the code actually crashed. But in my opinion, the increase to 128 cubed voxels, if we maintained the number of instances, so the actual number of simulations, because here I decreased the size of the simulation, but not the number of the simulations in the training set. If I increase the size of the simulations while keeping the number exact, probably the results could be worse. So because we have an higher dimensionality, so it would probably require us to also increase the number of simulations themselves. Nevertheless, with principal component analysis, even if we maintain the exact same number of simulations and increase the number of voxels, there should be the same number of principal components. So on the other side, I also believe that there is a great chance that the accuracy keeps being quite good. The only problem is that in the accuracy, even having the same number of principal components, is if the data shows a higher degree of nonlinearity, then it should be harder to compress and consequently to predict.
I see. Thank you. I think we have one question.
Yes, thank you very much for this talk. So I have, in fact, two questions, but I'll ask maybe just one, just to, echo to what you were mentioning. I mean, as you mentioned, Euclid and Vera-Rubin telescopes are going to seek for this very small scale, nonlinear regime in order to take advantage at most of it for cosmology. And as you discussed, I mean, there is a limitation in this regime. So do you see or do you foresee any possible improvement to get and seek these small scales that will be key for the cosmological interpretations?
Yes. If we, for example, trained our models using the bispectrum as our tuning parameter, as our evaluation metric, we could probably be able to reproduce the nonlinear aspects of the data quite well. In this case, we trained with the power spectrum only. So as you can see in the bispectrum picture, the quality of the results decreases quite a bit in all the cases. But if we adapted our code or improved our code to optimize our models with both the power spectrum and the bispectrum, we could probably reproduce quite well the nonlinear aspects of the data.
Okay, thank you very much. I don't know whether I can ask my second question or if it's too late.
Yes, you can ask. We have time.
Okay, thank you very much. So the second question is about the opening up of the parameters. So you've been opening up cosmological parameters, mostly focusing on omega dark matter. Are there any limitation to opening the other cosmological parameters of interest, and in particular the dark energy associated parameters that are key for the future large-scale surveys?
That's one already considered improvement to our methods, adding, for example, the AG2 or other relevant parameters like the spectral index, for example. I do not think there is an intrinsic limitation to adding those parameters. It's just a matter of, well, we are adding dimensionality by adding those parameters, so we should probably increase our data. But I don't think there is any intrinsic limitation on doing that apart from computational resources.
Okay, well, thank you again for your answers and for your talk. Thank you very much.
Thank you.
Okay, thank you again. So we go to the next presentation. Dr. Carvalho is
Yes.
unsupervised photometric detection of cluster candidates in large surveys. Please.
Hello, everyone. My name is Ana Carvalho, and I'm a first-year PhD student at Instituto de Astrofísica e Ciências do Espaço. And today I'm going to talk about unsupervised photometric detection of cluster candidates in large surveys. As we know, galaxy clusters are essential objects to test and constrain cosmology. However, the challenge lies in detecting them. And this is especially hard for large surveys, since there is a too much data to be analyzed. An example is the case for the Euclid survey, which it is expected to observe more than 60,000 clusters. So it is not possible to rely only on human power to analyze all of this data. And therefore we need unsupervised methods that can do so, but we also need methods that rely on minimal prior assumptions. And that also can work with photometry, which is also the information that we will have for the galaxies, since not all of them will be observed with spectroscopic instruments. So a method that does so for the case of stars is upmask, but I'm going to use for the first time here for galaxy clusters. Upmask stands for Unsupervised Photometric Membership Assignment in Stellar Clusters. It is a method that takes uncertainty of the catalog into account, and it is also an iterative process that uses PCA, K-means, and KDE. This is a flowchart of the method, but I'm going to explain how the method works right away. So we have our photometric data, and we are going to apply principal component analysis. Here I show the first 4 principal components for a simulated cluster, as well as the field galaxies within the same field of this simulated cluster. And on top of these 4 principal components, we are going to apply a clustering algorithm, in this case, the K-means. And this will group the galaxies that have similar photometric properties together. Afterwards, we are going to take each of this group and we are going to compare it with the random uniform distribution by applying for the 2 cases the kernel density estimation. So, and this will be, this kernel density estimation will be done with the spatial distribution, the right ascension and the declination. So if this group is compatible with belonging to a random uniform distribution, the points of this group will be removed from the process. If they were not, they will be kept. And then the method will iterate until no more points are being removed. So at the end of this stage, we will have points with assigned value of 0 if they are compatible with belonging to a random uniform distribution, and 1 if they were not. And we can also run this multiple times in order to have a frequentist membership probability. As some steps of this method can take quite some time, and so we have searched for alternatives in order to improve this time, namely the section that includes the KDE. And so here are the modifications or versions that we have attempted to implement. The first one uses a Voronoi tessellation. So we have here some galaxies of a cluster, and we want to compare it with the random uniform distribution. And this realization was made within the same area and number of points as our cluster. And so we apply our Voronoi tessellation, and we are going to take the areas of the distribution of the areas of each shape for both of these 2 cases, and we are going to compare it with the Anderson-Darling test. We can also do this comparison by comparing only a statistical parameter, in this case, the mean. So the third version that we have made is, instead of using a Voronoi tessellation, we are going to divide the space with the same subdivisions or cells. And then we are going to count the number of points that fall inside of each cell, and we are going to compare their distribution of counts for these 2 cases. And we can also do this, the part that the part of the random uniform realizations, we can do this outside of the method, since it only depends on the number of points. And so we do this fitting function in which we perform multiple tests according to number of objects, and we take the value that we pretend to. And so when we apply our method, it will take directly this threshold level instead of doing these realizations. And we can apply this same logic to the KDE case. So in order to validate our methods, and we have used simulated data. This simulated data comes from the mice catalog that is hosted in the Cosmology portal, in which we have selected one square degree of area. And then we have looked for the most massive cluster within this 1 square degree. We have selected these parameters in which the photometric information that we have collected is from Euclid filters. And so this cluster has 171 members and lies at Redshift 1.09. So we apply our method. Here I show the results for the KDE versions, the original method and the KDE and the fitting function. I also show here the spatial distribution of the points, in which I don't know if you can see, but they are very tiny, but the points, the opacity of the points corresponds to the frequentist membership probability that we have, that the method have computed. And I also show here the color map. This color map indicates the density of the points, and it was computed taking into account only the points that are above 50% of membership probability. And we have also computed the purity and the completeness curves according to this formula here for a given membership probability. And we see here that the KDE and the fitting function give similar results. So this means that we are applying the fitting function correctly. Here I show the results for the Voronoi versions. The first one, the Voronoi and the Anderson-Darling test, and the Voronoi and the mean comparison. We can see here already a big difference from the previous slide, which is that the completeness decreases a lot for the Voronoi and Anderson-Darling test. And this is due to the fact that the Anderson-Darling test is a much more strict comparison. But when we replace the Anderson-Darling test with a comparison of the means, we are able to improve the completeness. And finally, I show the results for the grid versions. The grid and the fitting function. Again, both of the cases give the same results, and the cures also give the similar results to the KDE. So it is now time to compare the CPU running time. Here I show a table for the times and the according versions, and overall we were able to improve the method, being the most successful improvement, the one with the Voronoi and mean comparison. But we are not only interested in improving time, we also want to study the impact of the parameters of the method with our results. And I start off by showing here, by listing the principal components of our simulated cluster data and their standard deviation. And their standard deviation is related to the amount of information that each component carries. Therefore, we can disregard all of the principal components that are below this data, this line, since their standard deviation is quite small. And so we are only going to take into account those below this line, these first 5 principal components, in which I show here the tests that we have made using only the first 2 components, the first 3, the first 4, and the first 5, as well as their CPU running time. And although for the last 2 cases using only 4 components or 5, there is only 20 seconds of difference, which is not much for only one application. These 20 seconds of difference can be very important if we apply this to large surveys. And on the other hand, the purity and the completeness curves for both of these 2 cases are not that much different. So we have chosen to use only the first 4 principal components. Afterwards, I show here the dependency of the number of k-means objects. These k-means objects is basically the average number that each group of the k-means will have. So as we increase this number, we see here that the completeness is increasing and the purity decreases, which can be explained by, again, the fact that we are increasing the number of objects per group. So in a way, we are being more complete. However, by adding more objects, the purity might decrease since we might be contaminating the group. And finally, I show here the dependency of the threshold level. This threshold level regulates the difference of the gap that we want in our comparison between the clustering group and the random uniform distribution. So as we increase this number, the purity overall is increasing as well, and the completeness is decreasing. So the conclusions for this part is that the Voronoi and the Anderson-Darling test improved time. However, it resulted in a more incomplete sample, and the Voronoi and the mean improved the completeness. We were also able to reduce the dimensionality to only 4 principal components, and you can adjust the parameters according to the different application that you want to have. So afterwards, we have searched for the Planck sources with our method, and we have done so by using the Pan-STARRS catalog. Here I show a spatial distribution of the Planck SC2 sources, which was the ones that we have used. And the black ones are those that fall inside the Pan-STARRS sky coverage. So we are going to select a field in the Pan-STARRS catalog around each of these black points. And so we apply our method to each of these fields. And if we classify a source as a cluster, if it has a field more than 10 members above 50% of membership probability, this is our distribution. This is for 70%, 90%, and 100%. Here I also show here the distribution of a detection with the Redshift. And here a detection is a field that has more than 10 members above 50% of membership probability. So here I show the distribution of the Zuneyev-Zeldovich flux with the Redshift, the histogram, and the fraction of those detected over the total number within the Pan-STARRS footprint for a given redshift bin. And we can see that there is only a weak dependency over the redshift range, except for the high redshift, but this is only due to the fact that for this range, there is only a small number of objects. And so we have compared our results or our findings with another work by Hone et al. From 2019. They have a project in which they are validating in the optical the Planck sources. And so we were able to find that there is 78 candidates, Planck candidates, that they have not observed node were able to validate. And therefore, we have investigated which ones that we have found were also studied by other authors. And so by performing this, after performing this search, we were able to find 67 cluster candidates that were not yet validated. And so the next step is to perform spectroscopic observation for these same 67 plane clusters. But we have seen that UpMask alone is able to identify new cluster candidates. And so the take-home messages are that we have presented an unsupervised method that uses statistical tools. And this supervised method can be used with galaxy clusters. Finally, being an unsupervised method, UpMask provides a very promising approach for automated identification of clustering large surveys. Thank you for your attention, and I'm happy to take any questions.
Thank you, Anna. Very nice slides.
Thank you.
Very nice, very good, well designed. Any comments and questions? So by your method, almost a double of the source that you can find. Doubled, yes?
Sorry?
May your method increase like double of the clusters compared to the traditional method on mask.
I didn't understand the question, sorry.
Oh, sorry, my question not important, but that not clear. Okay, please speak.
Okay, Nabila. So hello, thank you very much for your presentation and your talk. I have two questions, please.
Yes.
First one is when you use the k-means or any clustering method, you have to input the number of clusters that you have. How sensitive is the methodology to the number of clusters that you input in the k-means?
So basically is this study that we have done.
Yeah, sorry, it was going a bit fast, so sorry, yeah. Okay.
Oh, sorry.
No, sorry, okay, I see. Okay.
So the method, we have transformed the parameters in order to give us the average number of objects per k-means cluster, but not the number of clusters itself.
Okay, I see. Okay, fair enough. Second question is about the identification of the Planck clusters in pan-stars. So you've been using 10 members. My recalling of the identifications of clusters in optical is that 10 members for a cluster is a bit low in terms of reliability. So is this number of 10 more reliable in your approach, or is it just a conservative, or let's say like not a conservative but a liberal choice that you've been making?
Yes.
Can you comment on it, please?
Yes, we have chosen a small number only for identify new clusters. But obviously, if we want to further our studies, we might need to be more conservative. And although we are only using 10 members above 50% of membership probability, there can be probably the most reliable objects are also above this this percentage.
Yeah.
Yes. But it sounded like a nice classification for a first approach.
Okay, so it's kind of a first step and then going deeper into the...
Yes.
Okay, fair enough. Thank you very much.
Thank you.
Okay, anyone else? Okay, so thank you, Anna, again. Let's move to the last speaker. Hello?
Hey everyone, give me a second. Hi everyone, my name is Vazgen Vartanyan. I'm representing ICRANet Armenia. We're working on a machine learning based classification of blazar candidates of a certain type. So what is blazar? Blazars are radio loud active galactic nuclei with a relativistic jet pointing toward the observer. These sources are divided into two main classes, BL-Lecture objects, BLACs, and flat spectrum radio quasars, FSRQs, which shows very different optical spectra. In our research, we use 10 years.
Sorry to interrupt, because we hear some kind of echo if there is another laptop around or.
Give me a second. I will change room. Give me a second.
Okay.
Now it's better?
Yes, much better. But you should share your screen also.
Yeah, sure.
Okay. Thank you.
Yeah, about research. We use 10-year observation data from Fermi Large Area Telescope. This telescope has been continuously observing the gamma ray sky since 2008 August in 100 MeV to 300 GeV energy range. The latest Fermi Large Area Telescope's catalog lists around 5,800 gamma ray sources, about 700 more than the previous one. Out of these 5,800 sources, 3,437 are blazars. Around 1,200 are BLACs and 730 FSRQs. And we have about 1,500 blazar candidates of a certain type. If we compare the 4FGL with the previous lab catalog, we can see a significant increase in number of unclassified sources. The percentage of BCUs increased from 14% in first FGL to 44% in the last one. The increased difficulty to have sufficiently extensive optical observations campaigns for the classification of BCUs emphasize the importance of finding alternative ways to classify them. When optical spectra or multi-wavelength information needed for rigorous classifications are not available, a statistical approach to a problem, including machine learning, can be very useful for classification of VCUs. We use machine learning, and it's a method of recognizing pattern within data in order to achieve goals such as classification. In a type of machine learning called supervised machine learning, an algorithm classifies unknown objects by comparing their characteristics to characteristic of known objects. In our case, we use artificial neural networks, and they're basically a mathematical function over n-dimensional space, where n is the number of input parameters to the network. The parameters are values that describe the object, blazar in our case. Nm produces a likelihood for object to belong to a certain class. The network is trained on already classified objects, BLACs or FSRQs in our case. Therefore, for input parameters, we used gamma ray light curves and spectral energy distribution presented in 4FGL catalog. More precisely, we used 10 energy integrated fluxes corresponding to 1 year observation period, sorting by increasing value, and time integrated fluxes in 6 different energy ranges. This produces a set of 16 input parameters to the network for each sources. The 4FGL catalog contains time integrated fluxes in 7 energy bands from 0.05 to 300 GeV. We use 6 of them starting from the second one. A quick comparison between BLX and FSRQs shows several differences, like difference in slope, in average power loss index, where BLX having the lower one. And BLX on average have a higher flux values than FSRQs in highest energy bands and vice versa. Among the considered sources, some of them having missing data that is low test statistics in one of the measured energy intervals. In order to build a stronger network initially, we fill the missing data points using a machine learning algorithm. In order to fill the missing data points, we are divided our dataset into 4 different categories. Initially, as we can see on the left and the middle plots, the blazars can have power law and log parabola spectral shapes, which means their spectral properties are different. So at first, we need to divide them by spectral properties. Since our main goal is to classify also BLX and FSRQs, which by definition should have different spectral properties, we also divide blazars into source type categories. In total, we have 4 categories with division by spectra and division by classes. In the plots, you can see the original points and with low test statistics and the predicted points for the log parabola FSRQ model and 2 power low BLAC and FSRQ models. Besides the division into subset, we normalized our data by taking the ratio of original set point to its model's mid value, so that all our points vary around 0. As you can see, the method we have applied produces a result that's quite close to real values. For the imputation of missing data, we use the KNN algorithm. The idea in KNN method is to identify K samples in dataset that are similar or close in the space to our sample. Then we use the K samples to estimate the value of missing data point. Each sample's missing values are inputted using the mean value of K neighbors found in the dataset. We try more advanced methods, but as we have limited datasets around 1900 blazars, we know with known source types, more complicated missing data imputation algorithms stay underfitted. After implementing the KNN method and comparing its values from low test statistics from 1 to 2 TS range, we can see that our method can mimic the pattern of real data. The 4FGL catalogs also contains light curves with a bin duration of 1 year. This creates a set of 10 energy integrated fluxes for each source. Sorting the flux values from lowest to highest is one of the ways for making blazar activities comparable. The 10 annual time bins corresponding to 10 years of Fermi-Lat observation at random time intervals in the life of each blazar. We can see also differences in BLX and FSRQs in the light curves. Also, like BLX are on average dimmer than FSRQs in Fermi energy range. Their activities tend to be more continuous over time than FSRQs. For light curves, we can't use the imputation methods so we just fill missing points with zeros, normalize them, and sort by ascending order. Here you can see fluxes in the same observation time bin go into the same input node of our network. By sorting the flux values, we are directly comparing fluxes of dimmest, average, and brightest period for each blazar and the relationships between them. So after filling the missing data in spectral energy distribution and normalizing the light curves, we have the input parameters to build our network for classification. Initially, we applied cross-validation to test the model's ability to predict new data that was not used in estimating it, in order to flag problems like overfitting, selecting biases, and give the insights on how the model will generalize to an independent data set. In k-fold cross-validation, the data is divided into k subsets. After that method is repeated k times, such that each time one of the k subsets is used as the test and the other k-1 subsets are put together to form a training set. The error estimation is averaged over all k trials to get the total effectiveness of our model. As can be seen, every data point gets to be in a validation set exactly once and get to be in training set k-1 times. This significantly reduces bias as we're using most of our data for fitting, and also significantly reduces variance as most of the data is also being used in a validation set. After tenfold cross-validation training, we achieved 90.06% validation accuracy on our data set with a 2.24% error. The final network, in the final part, we create a network with 16 input neurons, 10 for yearly fluxes, and 6 for spectral energy distribution, with a hidden layer with 256 neurons and 2 output neurons with as a probability of source being BLAC or FSRQ. Before the classification of BCUs, we must fill the missing data of them. But here we can divide them only into spectral groups, power law and log parabolas. After that, the imputation algorithm will find the closest pattern for a particular source and correspondingly will fill the missing data. After the implementing of KNN method and comparing the values from low to statistics, we see that we can still mimic the pattern of real data. After filling in the missing data, we can classify the BCUs using our model. If we use cumulative precision metric of 90% for classification, we can classify 1034 BCUs as BLACs and 426 as FSRQs, leaving only 4 of them, 4 BCUs unclassified. If only highly probable candidates are selected, meaning that we select candidates only with precision higher than 90%, then 785 BCUs can be classified as BLACs and 278 as FSRQ. This classification corresponds to 98% cumulative precision for BLACs and 96 for FSRQs. Here you can see some of our results for specific BCUs that our network who have classified. The network can classify many more BCUs as almost certain BLUs than FSRQs. This is because some of BLUs occupy part of parameter space where there's no FSRQs, meaning that certain groups of BLUs are easily distinguishable from FSRQs. So our research has shown that we can develop a method that can classify blazars of uncertain type with higher confidence, which can be then used for studying their physical properties. Thank you very much. If you have any questions.
Thank you. I want to ask a question that why do you choose so sparse resolution? Like for the light curve, only 10 data points, and for the spectrum, only 6.
So, give me a second.
Yeah.
So we took only the 16 input parameters. After doing some research, we found, I will give reference papers that these particular parameters are most significant for classification task. So we took yearly fluxes because we have beside the yearly flux we can use 2-month integrated fluxes, but their information is have bigger errors. So we use the yearly fluxes, and the energy bands are selected because they're taking the biggest information part about the blazar. So
okay, thank you. Any other questions? Rahim?
Okay, thank you. Thank you to all participants. And thanks to the very fruitful presentation, which covers almost very large area of physics, from gravitational wave, astrophysics, and cosmology. Actually, this was the first time we ran this parallel session about artificial intelligence in Marcel Grossman meeting, which was very successful in my opinion. And I hope to have in the next Marcel Grossman meeting more parallel session and a plenary talk about this, and make people in this field of physics more aware of this very novel ways to attack the problems in regarding the huge amount of data that we can have. Thank you all. Thank you so much.
Okay, also for me, thank you very much for the reporters. I think machine learning in astronomy is a young field, and the speakers today are basically young people, always young mind. Today is a very good opportunity for everyone to get to know each other, and I hope we can collaborate in our future research, and we look forward to seeing you next time somewhere. Okay, I finished. So
okay.
anyone wants to
any comment? If there is any comment, we would be happy to hear. Otherwise, we can close this session. Okay, apparently there is no comment. Okay, goodbye. And thank you. Bye.